students, welcome to JSM. In previous videos, I have explained what is hybridization, formation of hybrid orbitals and different types of hybridizations. Different types of hybridizations. They are sp hybridization, sp2 hybridization, sp3, sp3d, sp3d2, sp3d3 hybridizations. Okay, in a particular hybridization the shape of the molecule and bond angle of the molecule is specific. That is, in case of sp hybridization, so geometry is linear, always linear, and bond angle is 180 degrees always. In case of sp3 hybridization, what is the geometry? Geometry is tetrahedral, and bond angle is 109 degrees 28 minutes. But in some of the molecules, these bond angle and geometries are deviating from their ideal geometries and bond angles. That means they are deviating from their original structure, deviating from their original bond angle. For example, in case of ammonia, so in the formation of ammonia, nitrogen undergoes sp3 hybridization. We know that if it is sp3 hybridization, bond angle is what? Bond angle is 109 degrees 28 minutes. And what is the shape? We know that tetrahedral. What is the shape? Tetrahedral. But in case of ammonia, what is the bond angle? Bond angle is 107 degrees. And geometry is pyramidal. What is the geometry? Geometry is pyramidal. So why it is deviation is taking place from their original bond angle and geometry? So now instead of 109 degrees 28 minutes, it is 107 degrees. Instead of tetrahedral, it is pyramidal. So to explain this, Sidgwick and Powell developed valence shell electron pair repulsion theory, and this is developed by Gillespie and Nyholm. So why it is the deviations are taking place from their regular geometries and bond angles? Just now we discussed in some of the molecules there is a deviation in bond angle and geometries from their regular bond angles and geometries. So reason is what? To explain this valence shell electron pair repulsion theory proposed by Sidgwick and Powell and developed by Gillespie and Nyholm. According to them, main postulates of VSEPR, that is valence shell electron pair repulsion theory. We know that if it is the central atom contains any lone pair, compulsory deviation occurs. There is no lone pair, so whatever geometry, whatever bond angle we predicted from hybridization, as it is present in that molecule. So that is the first point. The shape of the molecule is determined by repulsions between all of the electron pairs present in the valence shell. Okay, so right. Second point, in central atom valence shell, so there are two types of pairs are present. We know that first one is what? Lone pair, and second one is what? Bond pair. So now lone pair. So what is lone pair? The electron pair which is not involving in the bond formation and it is free from moving. They can easily move. Okay, so now electron pair which does not participate in bonding and it is free for movement. Okay, so now this is a free for movement. Okay, So now lone pairs. So lone pairs what? Free for movement. Free for movement. So next one is bond pairs. Okay. So what are bond pairs? Shared pair of electrons by which a covalent bond will form. Covalent bond will form. So these are the two types of pairs present at central atom in the valence shell. In the valence shell. So next, if central atom contains bond pairs along with that lone pairs are present, compulsory between them repulsions are taking place. Between them repulsions are taking place. So here, why repulsions are occurring between them? Lone pairs are occupying more space around the central atom. Lone pair of electrons or lone pairs occupying more space around the central atom. So that's why between lone pairs and bond pairs repulsions are occurring, repulsions are taking place. So that is the next point. Okay. According to Vsepr theory, that is Vsepr, there are different types of electron pairs. We know that in the valence shell of central atom. So compulsory between them repulsions are taking place. So now I am writing order of repulsions. Order of repulsions, that is lone pair causes more repulsions than lone pair bond pair, causes more repulsions than bond pair. This is the order of repulsions. This is the order of repulsions. Order of repulsions. Okay. Lone pair causes more repulsions than lone pair bond pair, causes more repulsions than bond pair. Bond pair. Okay. So next one. If it is the molecule having all bond pairs, there is no lone pair. Okay, the molecule having bond pairs only, the geometry and bond angle is regular. What we predicted from hybridization? And this is the molecule is known as what? Regular hybridization, that is a regular bond angle, and geometry also ideal, that is ideal or regular geometry. Say for example, this is a methane. I am taking all our bond pairs. Here it is the zero lone pairs. So now what is the hybridization? sp3 hybridization. Once we know sp3 hybridization, what is the bond angle? 109 degrees 28 minutes. And what is the geometry? Tetrahedral geometry. Okay. If all are bond pairs, there is no deviation. Okay. So right. Next point. If the molecule, that is the central atom in a molecule contains bond pairs along with that lone pairs, compulsory there is a deviation takes place. From their regular geometry and regular bond angles. So that is the last point. If the molecule contains lone pairs along with bond pairs, then the actual geometry of the molecule will be different from what we predicted from hybridization. Okay, what we predicted from hybridization. Compulsory lone pair causes repulsions on bond pair. Lone pair occupies more space around central atom. So that is the lone pair causes repulsions between bond pairs. So these are the bond pairs are moving towards each other. So there is a deviation in bond angle and geometry also takes place. So that is the last point. Here bond angle. So bond angle is inversely proportional to the repulsions present between lone pairs. So these are the main postulates of valence shell electron pair repulsion theory. Thank you.